You know, every single structure around us, from a massive skyscraper to a tiny paperclip, is in a constant battle with invisible forces. Today, we're going to make those forces visible. We're going to break down the concept of stress, which is really the internal language that tells us if a bridge is going to stand or if a machine is about to fail. Okay, let's dive right in. I want you to imagine zooming way, way down, deep inside any solid object, until we can isolate a teeny tiny microscopic cube. Now think of this little cube as a single point in space, with dimensions we can call delta x, delta y, and delta z. But this isn't just some boring geometric shape. No, it's a snapshot of all the pushes, all the pulls, and all the twists happening at that one specific point, all at the same time. And here's where it gets kind of crazy. Before we apply a single law of physics, this tiny element is being hit by a chaotic swarm of forces. I mean, on each of its 6 faces, forces can act in 3 different directions. If you do the math, that adds up to a staggering 18 initial stress components, all bombarding this one tiny point. So, our first job is to somehow bring order to this chaos. And to do that, we've got to carefully identify and categorize exactly what we're dealing with. It sounds complicated, I know, but trust me, there's a really beautiful logic hiding under all this complexity. It turns out all 18 of these components fall into 2 main families. We've got 6 what we call normal stresses. Think of these as direct pushes and pulls. And then we have 12 shear stresses, which are more like slicing or sliding forces. All right, let's tackle the normal stresses first. We use the Greek letter sigma for these. These are the forces that act perpendicular, or normal, to each face of our little cube. So you've got one for the front and back, one for the top and bottom, and one for the left and right sides. That's 3 pairs, which gives us our 6 normal stress components. Simple enough, right? And then you've got the shear stresses, which we represent with tau. These guys act parallel to the faces of the cube, and they're always trying to distort its shape. On any given face, you can have a shear going, say, up and down or left and right. So with 2 possible shear directions on each of the 6 faces, yep, that's where we get our 12 shear stress components. So the key takeaway here, the whole ballgame, is direction. Normal stresses are perpendicular. They're trying to stretch or squash the cube. Shear stresses are parallel. They're trying to slice it or smear it out. It's really the difference between pulling on a rope versus sliding a book across a table. Okay, let's be real. 18 separate components, that's just way too much information to be useful. You can't design an airplane wing by tracking 18 different values at every single point. It's just not practical. But this is where the pure elegance of physics comes in. It lets us slice right through this complexity with 2 fundamental and honestly beautiful laws. So, our first tool for simplification is a really simple but powerful idea. For our tiny cube to just be sitting still, all the forces acting on it have to be perfectly balanced. We call this force equilibrium. I mean, think about it, right? If the push on the front face was even slightly stronger than the push on the back face, our little cube would go shooting off through the material. But it doesn't. So we know the normal stress on the front has to exactly equal the normal stress on the back. And the same logic applies to all the shear stresses too. And because those forces on opposite faces are just mirror images of each other, we don't need to track them separately. And just like that, boom, we've cut our problem in half. We've gone from 18 messy components down to a much nicer 9. Okay, cutting it down to 9 is a huge step. But guess what? We can do even better. Because our little cube isn't just sitting still, it's also not spinning wildly in place, right? This means all the twisting forces, what we call moments, they also have to cancel each other out. Now, to keep the cube from spinning, the twisting forces also have to be in perfect balance. And this leads to a really cool consequence. It means the shear stress on, say, the top face that's pushing to the right must be equal to the shear stress on the right face that's pushing up. This simple requirement proves that pairs of these shear stresses, like tau xy and tau ix, they have to be identical. So that symmetry means 3 more of our shear stresses are redundant. They're just duplicates. We don't need them. We boiled everything down from 9 to the final magic number, just 6. These 6 values, that's all we need. That's the whole shebang, everything required to completely define the stress at a single point. So let's recap. We've taken this totally chaotic physical reality with 18 different forces, we applied 2 basic laws of physics, and we found this beautiful underlying simplicity. The question now is, what do we do with these 6 numbers to make them useful? How do we package them? And this right here is the payoff. These 6 components, our 3 normal stresses and our 3 unique shear stresses, they fit perfectly into this elegant mathematical object called the stress tensor. It's just a simple 3 by 3 matrix, but it completely and totally describes the complex state of stress at any point in a material. It's awesome. So why does this matter? Who cares? Well, we care because with this one single compact tool, engineers can analyze forces from any direction. It's like a universal translator for stress. It lets us predict how, and more importantly, when a material is going to bend, deform, or just plain break. But hold on, here's the ultimate simplification, the final magic trick. For any state of stress, no matter how complex, the math of the tensor lets us find a special angle, a unique orientation, where all those complicated shear stresses, they just vanish. They go to zero. When we rotate our view to what we call these principal axes, all we're left with are pure, direct push/pull forces. These are the points of maximum tension and compression, and they tell us exactly where a material is weakest. So we've gone on this incredible journey from total physical chaos to clean mathematical order. We've turned a swarm of 18 forces into one powerful tool. We now have the language to describe stress. But the real question, the one that keeps engineers up at night, still remains. When does this elegant order finally break? And what does that failure actually look like?